Everything you have ever seen with your own eyes, every star that has ever caught your attention on a clear night, every galaxy ever captured by a telescope, exists inside a bubble roughly 93 billion light-years across. That number alone should stop you. Not 93 billion light-years away, which would already be almost incomprehensible, but 93 billion light-years wide, an entire sphere of space with Earth sitting quietly near its center, simply because that is how far light has managed to travel since the universe began. And here is the part that rarely gets said out loud. This sphere is not the universe. It is only the part of the universe we are physically capable of detecting. Somewhere beyond that boundary, galaxies are forming, stars are dying, and entire clusters of matter are doing everything ours are doing, and we will never see a single photon of light from any of it. Not because our telescopes are not good enough, not because we have not looked hard enough, but because the universe itself has made it physically impossible. That single fact sits at the center of one of the strangest situations in all of science. We live inside a cosmos that may be infinite, or so close to infinite that the difference barely matters. And yet the tools we use to study it, telescopes, satellites, mathematics, all of them run into a wall that cannot be pushed back, no matter how advanced our civilization becomes. This is not a temporary limitation waiting for better engineering. It appears to be a permanent feature of reality. And once you understand why, you start to see the universe differently, not as a place we are slowly mapping in full, but as a place where the vast majority of what exists will remain forever unconfirmed, sitting just past a horizon we can calculate but never cross. To understand why this boundary exists, you have to start with something most people never think carefully about. Light is fast, but it is not infinite. It travels at roughly 299,792 kilometers per second, a number so large in everyday terms that it feels instantaneous, a flashlight beam reaching a wall seemingly the moment you flip the switch. But scale that speed up to cosmic distances and suddenly it becomes agonizingly slow. Light from the sun takes about 8 minutes to reach Earth. Light from the next nearest star system, Alpha Centauri, takes over 4 years. And light from the most distant galaxies we can observe has been traveling for more than 13 billion years, meaning when we look at those galaxies through a telescope, we are not seeing them as they are today. We are seeing light that left them before Earth even existed, a fossil image frozen mid-transmission and only now arriving at our detectors. Long before anyone had measured the speed of light with modern precision or discovered cosmic expansion, a much simpler observation had already hinted that something was strange about treating the universe as infinite, unchanging, and eternal. It goes by the name Olbers paradox after the German astronomer Heinrich Olbers, who popularized it in the early 1800s, although earlier thinkers including Johannes Kepler and Edmund Halley had wrestled with versions of the same puzzle. The reasoning is simple enough to follow without any equipment at all. If the universe is infinite in extent, populated with an essentially endless number of stars scattered more or less evenly throughout, then no matter which direction you look, your line of sight should eventually strike the surface of some star, however distant. Every patch of the night sky should therefore appear roughly as bright as the surface of an average star, meaning the sky should blaze with light in every direction, day and night alike. And yet plainly, it does not. The night sky is mostly dark, with only scattered points of starlight against a black background. Something in the assumption of an infinite, unchanging, eternal universe had to be wrong. The resolution, though not fully appreciated until the 20th century, turns out to connect directly to everything already discussed. The universe is not eternal in the way Olbers assumed. It has a finite age, meaning light from sufficiently distant stars and galaxies simply has not had time to reach us yet, regardless of whether the universe extends infinitely in space. Combine that with cosmic expansion, which redshifts the light from very distant, very old sources down into wavelengths our eyes cannot perceive as visible brightness. Stretching what would have been intense visible or ultraviolet radiation from the early universe into the microwave background, we detect with radio instruments rather than see with our eyes. And the darkness of the night sky stops being a paradox at all. It becomes, in hindsight, one of the simplest and most accessible pieces of evidence available to anyone, without a telescope, without a satellite, just by looking up, that the universe has both a finite age and a history of change, rather than being an infinite, static, eternal backdrop. It is a nice reminder that some of the deepest cosmological puzzles have always been available to ordinary human observation, waiting for the right theoretical framework to make sense of them. This delay is the entire foundation of how astronomers study the past. Every telescope is, in a very real sense, a time machine, not because it moves us through time, but because everything it observes is already history. The deeper we look into space, the further back in time we are seeing. And this brings us to the age of the universe itself, currently estimated at around 13,800,000,000 years, based on multiple independent lines of evidence including the cosmic microwave background, the oldest light in existence, dating back to roughly 380,000 years after the beginning of everything. If light has only had 13,800,000,000 years to travel since the earliest moments of the cosmos, it seems like the observable universe should be a sphere with a radius of 13,800,000,000 light-years. That would be the intuitive answer. It is also wrong, and the reason it is wrong reveals something profound about the nature of space itself. Space is not a static backdrop that things move through. Space itself has been stretching since the beginning of the universe, a discovery that reshaped cosmology in the 20th century. While a photon of light was making its 13,800,000,000 year journey toward Earth, the space between that photon's origin point and its destination was expanding the entire time, like a rubber sheet being pulled apart from every direction at once. By the time that ancient light finally reaches our telescopes today, the galaxy that originally emitted it is no longer 13,800,000,000 light-years away. Because of that ongoing expansion, it is now, right now, at this very moment, approximately 46,500,000,000 light-years away. Double that distance to account for both directions from Earth, and you get the true diameter of the observable universe, close to 93 billion light-years. This is a good moment to address a persistent misconception that the phrase Big Bang itself tends to encourage. The image of a localized explosion, matter and energy blasting outward from a single point into an already existing, empty surrounding space. The way an explosion on Earth sends debris flying outward into the air around it. That picture is simply not what the evidence describes. The Big Bang did not happen at a specific point within space. It happened everywhere at once because in the earliest moments of the universe, all of space itself, everywhere that would ever exist, was compressed into that hot, dense state simultaneously. There is no special point you could travel to and identify as the location where the Big Bang occurred, any more than there is a special point on the surface of that inflating balloon from earlier that could be identified as the balloon's center of expansion. Every point in space, including the point you are occupying right now, was part of that early, hot, dense state, and every point has been expanding away from every other point ever since. This distinction matters enormously for correctly understanding cosmic expansion, because it clarifies that when astronomers describe the distance to a very early, very distant galaxy, they are usually referring to what is called co-moving distance. Essentially, the distance calculated by removing the effect of the ongoing expansion, describing the underlying grid of space itself, rather than the constantly changing physical separation between two objects at any single moment in time. It is a subtle but important technical distinction, and it is precisely the reason cosmologists can meaningfully talk about a galaxy's light having traveled 13 billion years to reach us, While that same galaxy's current physical distance is now over 46 billion light-years away, two different, equally valid numbers describing the same object. Depending on whether you are measuring light travel time or present-day physical separation across an expanding grid, that already reframes everything. The observable universe is not simply a record of how long light has had to travel. It is a snapshot shaped by an expanding stage on which that journey took place. And once you accept that the space itself is stretching, you have to ask an uncomfortable question. If space has been expanding for the entire history of the universe, and if it is still expanding today, what does that mean for everything sitting beyond our 93 billion light-year bubble? Here is where the story stops being about distance and starts being about disappearance. There is an ironic twist buried in this story that is worth telling, properly before we get to Hubble himself. When Einstein first applied his own equations of general relativity to the universe as a whole in 1917, he ran into a problem. His equations, left on their own, predicted a universe that should either be expanding or contracting, not sitting still, because the mutual gravitational attraction of all the matter within it would inevitably cause a collapse unless something counteracted it. At the time, the prevailing assumption, shared by essentially every astronomer including Einstein himself, was that the universe was static, eternal, and unchanging, an assumption rooted more in intuition and limited observational evidence than in any rigorous proof. To force his equations to describe a static universe, Einstein introduced an additional term, a constant value representing a kind of repulsive pressure built into space itself, precisely calibrated to balance out gravity and hold the universe still. He called it the cosmological constant. When Hubble's observations later revealed the universe was, in fact, expanding, Einstein reportedly regretted introducing the term, allegedly calling it his biggest blunder, a story that may be somewhat embellished in the retelling, but captures a real historical moment nonetheless. Since a genuinely expanding universe no longer needed an artificial balancing term to prevent collapse. For decades afterward, the cosmological constant was treated as a historical footnote, a mistake abandoned once its original purpose evaporated. Then, in the late 1990s, when the accelerating expansion of the universe was discovered, physicists realized that a term with exactly the same mathematical form as Einstein's abandoned cosmological constant was precisely what was needed to explain the acceleration, not to hold the universe static, but to actively push it apart at an increasing rate. Einstein's supposed blunder turned out to be, in a sense, decades ahead of the observational evidence required to justify it, a strange full-circle moment in the history of physics that still surprises people encountering it for the first time. In the 1920s, an American astronomer named Edwin Hubble made an observation that would eventually unravel humanity's entire picture of a static, unchanging cosmos. Using the largest telescope of his era at Mount Wilson Observatory in California, Hubble discovered that distant galaxies were not just sitting in place. Their light was shifted toward the red end of the spectrum, a phenomenon called redshift, and the further away a galaxy was, the more dramatic that redshift became. The conclusion was unavoidable. Distant galaxies were receding from us, and the ones farther away were receding faster. This relationship, now known as Hubble's law, became one of the most important discoveries in the history of astronomy because it implied something almost too large to process. If everything is moving apart from everything else, then the universe itself must be expanding, and if you run that expansion backward in time, everything must have once been compressed into an incredibly hot, dense state. Hubble had stumbled onto the first observational evidence for what would eventually be called the Big Bang. But Hubble's discovery contained a second, quieter implication that took decades longer to fully appreciate. If galaxies are receding faster the farther away they are, there should be some distance at which a galaxy's recession speed reaches the speed of light. Beyond that point, logic seems to break down because nothing, according to Einstein's theory of relativity, can travel faster than light, except that rule does not actually apply here. And understanding why requires clearing up one of the most common misconceptions in popular science. Einstein's speed limit applies to objects moving through space. It does not apply to space itself. A spaceship cannot accelerate past the speed of light relative to its local surroundings, no matter how powerful its engines are. But the fabric of space between two distant points can stretch at any rate, unconstrained by that same limit, because nothing is actually moving through anything. The distance itself is simply growing. Two galaxies can be receding from each other faster than light without either one ever locally breaking a single law of physics, because neither galaxy is doing the moving. The space between them is doing the moving, and space plays by different rules. Hubble was not actually the first to notice this pattern of galaxies rushing away from us. A less celebrated astronomer named Vesto Slipher, working at Lowell Observatory in Arizona more than a decade earlier, had already measured redshifts in a number of what were then called spiral nebulae, objects whose true nature as separate galaxies far beyond our own Milky Way was not yet understood or accepted. Slipher painstakingly recorded that most of these objects showed redshift, meaning they appeared to be moving away but without a reliable way to measure how far away they actually were. The significance of the pattern remained unclear. What Hubble contributed was the missing piece, distance, and he was only able to supply it because of a discovery made a decade before that by a woman whose name deserves to be far better known than it is. Henrietta Swan Leavitt worked at the Harvard College Observatory in the early 20th century, part of a team of women hired to catalogue and measure photographic plates of stars, work considered too tedious for the male astronomers of the era, who nonetheless produced some of the most consequential discoveries in the field's history. Studying a class of pulsating stars called Cepheid variables, stars whose brightness rhythmically rises and falls over periods ranging from days to months, Leavitt noticed something remarkable. The length of a Cepheid's pulsation period was directly related to its true intrinsic brightness, its luminosity. A Cepheid that pulsed slowly was reliably brighter than one that pulsed quickly. This relationship meant that if you could measure how long a Cepheid took to complete a pulsation cycle, you would know its true brightness, and by comparing that true brightness to how dim it appeared from Earth, you could calculate exactly how far away it was, since light dims in a predictable, calculable way as distance increases. Leavitt had effectively handed astronomy a cosmic ruler, a way to measure distances to objects far beyond what parallax, the traditional method of measuring a star's apparent shift in position as Earth orbits the Sun, could ever reach. Parallax only works for relatively nearby stars because the shift becomes too small to measure accurately beyond a certain distance. Cepheid variables extended that ruler dramatically further into space. It was this exact technique that Hubble used to measure the distance to what was then called the Andromeda Nebula, finding a distance so enormous that it settled a major scientific debate of the era, sometimes called the Great Debate, over whether these fuzzy spiral objects were relatively small structures within our own Milky Way or entirely separate galaxies in their own right, island universes located millions of light years away. Hubble's measurement proved decisively that Andromeda, and by extension countless other spiral nebulae, were indeed separate galaxies, instantly expanding the known scale of the universe by many orders of magnitude, before he then went on to combine these distance measurements with Slipher's redshift data to establish the relationship between distance and recession velocity that now bears his name. This method, using objects of known calculable brightness to measure cosmic distances, became known as the cosmic distance ladder, with different types of objects serving as reliable distance markers at different scales. Cepheid variables for relatively nearer galaxies, and eventually a specific type of exploding star called a Type 1a supernova for far more distant ones. These supernovae occur when a dense stellar remnant called a white dwarf, in a binary system with a companion star, gradually pulls in enough material to cross a very specific mass threshold, causing a runaway thermonuclear explosion of remarkably consistent intrinsic brightness across the universe. Because that brightness is so predictable, these supernovae function as what astronomers call standard candles, objects whose known true brightness allows precise distance calculation no matter how far away they occur. It was precisely this technique, applied to dozens of distant Type 1a supernovae in the late 1990s by two independent research teams, that revealed the universe's expansion was not slowing under its own gravity as everyone expected, but accelerating. The discovery that introduced dark energy into modern physics and reshaped every subsequent conversation about the ultimate fate and scale of the cosmos. This distinction sounds like a technicality, but it has staggering consequences. It means that right now, at this exact moment, there are galaxies whose light emitted today will never reach Earth, no matter how much time passes. No matter how advanced our instruments become a million years from now. The space between us and those galaxies is stretching faster than light can cross it. Cosmologists call the boundary marking this point the cosmological event horizon, and it functions almost exactly like the event horizon of a black hole. Except instead of gravity trapping light inside a small region, cosmic expansion is preventing light from ever crossing a growing gulf between us and everything beyond that boundary. It helps to have a mental picture for what is actually happening here, because the phrase space is expanding tends to conjure the wrong image, something like an explosion hurling debris outward into an already existing empty void. That is not what cosmologists mean. A more useful analogy, imperfect as any analogy is, involves a loaf of raisin bread rising in an oven. Imagine each raisin representing a galaxy embedded in dough that represents space itself. As the dough rises, every raisin moves farther away from every other raisin, not because the raisins are traveling through the dough under their own power, but because the dough itself, the space between them, is expanding. And crucially, a raisin farther from any given point will separate from it faster than a nearby raisin, simply because there is more expanding dough between them to add up. This is exactly the relationship Hubble discovered, recession speed increasing with distance, and it falls naturally out of uniform expansion happening everywhere at once, without requiring any special central point from which everything is fleeing. There is no center to the expansion of the universe in the way there is a center to an explosion. Every point can, in a meaningful sense, be treated as the center, because every observer on every raisin in every galaxy would see the same pattern, everything else rushing away, with more distant things receding faster. A second helpful image involves the surface of an inflating balloon with dots drawn across it, representing galaxies. As you blow air into the balloon, every dot moves away from every other dot along the curved two-dimensional surface, again without any single dot occupying a privileged central position. The balloon analogy also helps illustrate the flatness question from earlier, since the surface of a balloon is a curved, two-dimensional analog for a positively curved universe, useful specifically because it lets us visualize curvature in a lower number of dimensions than the actual three-dimensional space we inhabit, which we cannot directly visualize curving in the same intuitive way. It is worth noting that professional cosmologists themselves lean on these same simplified pictures constantly, not because the underlying mathematics is beyond them, but because human intuition, shaped entirely by everyday experience at ordinary speeds and ordinary distances, simply did not evolve to natively grasp concepts like space-time curvature or distances growing without anything moving through space. Building a working mental model, even an imperfect one, is often the only practical way to reason productively about phenomena this far outside normal human experience. And it is a big part of why analogies like these show up so often in both classrooms and research seminars alike, not merely in popular explanations aimed at a general audience. Every analogy like this breaks down eventually if pushed too far. Dough and balloon rubber are physical materials existing within a larger three-dimensional space, whereas cosmic space is not understood to be expanding into anything at all. It is simply the distances within it that are growing. But, used carefully, these images make an otherwise deeply counterintuitive phenomenon feel almost tangible. If this feels unsettling, you are reacting appropriately. It means the universe is not simply large. It is actively erasing itself from our potential view, region by region, galaxy by galaxy, forever. And this is not a one-time event. It is ongoing right now as you listen to this. Galaxies that our great-grandchildren's telescopes could theoretically have observed will, by then, have crossed the horizon and vanished from all possible detection. Their light forever chasing a destination that keeps outrunning it. The comparison to a black hole's event horizon is not merely a loose figure of speech. It reflects a genuine mathematical kinship discovered decades before dark energy itself was confirmed. In the years immediately following Einstein's publication of general relativity, Dutch astronomer Willem de Sitter worked out a solution to Einstein's equations, describing a universe containing no matter at all, empty except for a form of energy embedded in space itself, mathematically identical in form to what we now call the cosmological constant. De Sitter's solution, initially treated as a curious mathematical exercise rather than a description of physical reality, since the actual universe obviously contains matter, produced a universe that expands exponentially forever, and crucially, produced its own horizon, a boundary beyond which no signal could ever reach an observer, purely as a consequence of that relentless exponential expansion. For decades, this remained a mathematical curiosity, a toy model interesting to relativists but seemingly disconnected from the observed universe, which appeared to contain enough matter that its gravity should be slowing expansion down, not accelerating it exponentially. When the accelerating expansion of our actual universe was confirmed observationally in the late 1990s, cosmologists realized that de Sitter's decades-old toy model was no longer just a mathematical exercise. It was, in the distant future at least, an excellent approximation of where our own universe is headed. As matter continues to dilute across an ever-expanding volume, while dark energy's influence, tied to the volume of space itself rather than the amount of matter within it, comes to dominate ever more completely. Our universe today is not yet a pure de Sitter universe. Matter and radiation still play a meaningful role in its dynamics, but on sufficiently long timescales, trillions of years into the future, models suggest it increasingly will resemble one, expanding exponentially into a dark, cold, and increasingly empty future, surrounded by a horizon that keeps drawing inward around whatever gravitationally bound structures remain. This is the moment worth pausing on, because it changes the entire emotional weight of everything that follows. If this idea that most of reality may be permanently unreachable is the kind of thing that keeps your mind turning after you close a tab, it is worth taking a moment now to make sure you do not lose this thread, because the deeper implications only get stranger from here. To understand exactly how much we stand to lose and how fast, scientists needed a precise measurement of how quickly space is expanding. That number is called the Hubble constant, and pinning it down has become one of the most contentious and fascinating pursuits in modern cosmology. Different measurement techniques, one based on the cosmic microwave background from the early universe, another based on the brightness of exploding stars called supernovae in the more recent universe, have produced two different answers that refuse to agree with each other, a discrepancy researchers now call the Hubble tension. One method suggests space is expanding at roughly 67 kilometers per second for every megaparsec of distance, a distance unit equal to about 3,260,000 light-years. The other method suggests a rate closer to 73 kilometers per second per megaparsec. That may sound like a minor disagreement, but in cosmology, a persistent unexplained gap between two independently verified measurements often signals that something fundamental is missing from our understanding of physics, not just our arithmetic. Some researchers suspect an unknown property of dark energy. Others wonder if there is a flaw in how we interpret the early universe. As of now, the tension remains unresolved, an open wound in one of science's most successful models. Whichever value turns out to be correct, the underlying reality does not change. Space is expanding and it appears to be accelerating, a discovery that shocked cosmologists so thoroughly when it was confirmed in the late 1990s that it earned the Nobel Prize in Physics in 2011 for the teams involved. Before that discovery, most physicists assumed the gravitational pull of all the matter in the universe would be gradually slowing the expansion down, perhaps even eventually reversing it into a collapse sometimes nicknamed the Big Crunch. Instead, observations of distant supernovae revealed the opposite. The expansion of the universe is speeding up, driven by a mysterious force now called dark energy, which appears to make up roughly 68% of the total energy content of the universe. We do not know what dark energy actually is. We can measure its effects with remarkable precision, but its underlying nature remains one of the biggest open questions in physics, arguably the biggest. Before going further, it is worth clearing up a common point of confusion. Because dark energy is frequently mixed up with a completely different mystery, dark matter and the two, despite sharing a name pattern, describe entirely different phenomena. Dark matter refers to an invisible form of matter, detected only through its gravitational influence, that appears to make up roughly 27% of the universe's total energy content, vastly outweighing the ordinary atomic matter that makes up stars, planets, and everything we can directly see, which accounts for only around 5%. Evidence for dark matter comes from multiple independent directions. The rotation speeds of stars orbiting within galaxies, which move far too fast to be held in place by the gravity of visible matter alone, a discrepancy most decisively documented in the 1960s and 70s by astronomer Vera Rubin, working alongside Kent Ford, whose careful measurements of the rotation speeds of stars at varying distances from the centers of spiral galaxies found that stars far out at the galactic edge were orbiting just as fast as those much closer in, a pattern flatly inconsistent with the distribution of visible matter, which should have caused outer stars to orbit noticeably slower, mirroring how outer planets in our own solar system orbit the Sun more slowly than inner ones. Rubin's work, initially met with some skepticism, gradually became recognized as some of the most compelling observational evidence for the existence of a large, invisible mass component surrounding galaxies. Work later honored by NASA naming the Vera C. Rubin Observatory after her, the same facility now conducting the decade-long sky survey we mentioned earlier in connection with dark energy research. The way galaxy clusters bend and distort light passing near them through a phenomenon called gravitational lensing, and the specific pattern of those temperature fluctuations in the cosmic microwave background, which would look different if dark matter did not exist to help gravitationally amplify the small initial density variations left over from the early universe. Dark matter's gravitational pull is attractive, behaving in most respects like ordinary matter, just without emitting or absorbing light, and it acts as a kind of invisible scaffolding, helping ordinary matter clump together into the galaxies and galaxy clusters we observe today. Dark energy, by contrast, is not a form of matter at all in any conventional sense. It behaves like a property of space itself, and rather than pulling things together, its effect is repulsive on cosmic scales, driving the accelerating expansion we have been discussing throughout. Put simply, dark matter builds structure while dark energy tears space apart. Together, along with the roughly 5% ordinary matter, these three components make up what cosmologists call the standard model of cosmology, sometimes abbreviated lambda cold dark matter, where lambda represents the mathematical symbol Einstein originally used for the cosmological constant, the simplest theoretical description of dark energy. This model has proven remarkably successful at explaining an enormous range of observations, from the fine structure of the cosmic microwave background to the large-scale distribution of galaxies across the observable universe. Even though the fundamental nature of two of its three main ingredients remains almost entirely mysterious, this acceleration is directly responsible for the cosmological event horizon growing more restrictive over time, not less. It would be reasonable to assume that as humanity develops better telescopes, we simply see more of the universe, chipping away at the mystery bit by bit. And in one sense, that is true. Improved instruments can detect fainter, more distant light that already exists within our reach. But because the expansion is accelerating, the boundary marking what will ever be reachable is, from our perspective, effectively closing in. Galaxies currently visible to us today, whose light is currently crossing the gap and arriving at our telescopes, are, at this very moment, crossing into recession speeds that will eventually place them permanently beyond any possible future detection. Right now, we can still see somewhere on the order of hundreds of billions of galaxies within the observable universe, with some statistical extrapolations from deep field imaging pushing that estimate as high as 2 trillion, though the exact figure remains genuinely debated and continues to be revised as survey techniques improve. But models of cosmic expansion suggest that in the extremely distant future, over trillions of years, an observer in the Milky Way's remnant would eventually see nothing beyond a single, isolated cluster of gravitationally bound galaxies, with everything else having redshifted into permanent invisibility. The rest of the universe, from that future vantage point, would appear to simply not exist. This ongoing refinement of galaxy counts is itself a story worth pausing on, because it illustrates something important about how deep field astronomy actually works. The original 2 trillion galaxy estimate came from a statistical technique, extrapolating the density of galaxies visible in the deepest available Hubble images outward across the whole sky, and assuming that fainter, more distant galaxies too dim to detect directly would continue to follow the same statistical pattern seen in slightly brighter, closer ones. When the James Webb Space Telescope launched at the end of 2021 and operating at infrared wavelengths particularly suited to detecting the stretched, redshifted light of very early galaxies, began returning data from unprecedented depths of the observable universe, it produced a genuine surprise. Rather than confirming an ever-increasing density of faint galaxies at greater distances exactly as extrapolated, Webb found a population of galaxies in the very early universe, within the first several 100 million years after the Big Bang, that appeared considerably more massive, more structured, and more numerous than most theoretical models had predicted was possible in such a short span of cosmic time. Some early headlines described this as breaking cosmology altogether, a framing that overstated the situation considerably. What actually happened is that astrophysicists are still working through several competing explanations, ranging from more efficient early star formation than previously modeled, to black holes contributing unexpectedly large amounts of light in these early systems, to more modest adjustments in how galaxy formation timelines are calculated. It remains an active, unresolved area of research, a genuine example of new data outpacing existing theory and forcing scientists back to the drawing board, precisely the kind of productive friction that drives the field forward rather than a crisis undermining its foundations. We are, cosmologically speaking, living in a surprisingly good era to be doing astronomy. Earlier in the universe's history, structures had not yet formed enough for this kind of observation to even be meaningful. Far enough into the future, the sky itself will have gone dark beyond our immediate galactic neighborhood. We happen to exist in the narrow window where the observable universe is rich enough with visible structure to actually study, and that window is, on cosmic timescales, closing. This is precisely the kind of question modern instruments are racing to pin down with greater precision. NASA's Nancy Grace Roman Space Telescope, named for the astronomer often credited as the driving force behind the creation of the Hubble Space Telescope program, is scheduled to launch in the latter part of 2026. carrying a field of view roughly 100 times wider than Hubble's while maintaining comparable image sharpness. Its primary scientific goals include mapping the distribution and behavior of dark energy across cosmic history with unprecedented precision, using surveys of billions of galaxies to measure how expansion has changed over billions of years. Alongside it, the European Space Agency's Euclid mission, already collecting data since its launch in 2023, is conducting a similarly ambitious survey, mapping the large-scale structure of the universe across more than a third of the sky to constrain the properties of dark energy and dark matter. And on the ground, the Vera C. Rubin Observatory in Chile, having begun its decade-long survey of the southern sky, is generating one of the largest and most detailed maps of cosmic structure ever assembled, repeatedly imaging the entire visible sky every few nights to catch changes, transient events, and subtle patterns in how galaxies are distributed. None of these instruments will let us see past the cosmological horizon. That barrier is not a limitation of resolution or sensitivity. It is built into the geometry of an expanding universe itself. But together, these observatories are refining exactly how fast that horizon is closing and how much of the universe we can expect to lose access to as centuries and millennia pass. It is worth mentioning that light is no longer the only messenger astronomers rely on to study the universe, and this matters directly for how researchers hope to eventually test some of the ideas we have been discussing. In 2015, the Laser Interferometer Gravitational Wave Observatory, commonly known as LIGO, made the first direct detection of gravitational waves, ripples in the fabric of space-time itself, predicted by Einstein a full century earlier, produced in that instance by the collision of two black holes over 1 billion light-years away. Unlike light, which can be absorbed, scattered, or blocked by intervening matter and dust, gravitational waves pass through the universe essentially unimpeded, carrying information about their violent origins with almost no distortion along the way. This opened an entirely new observational channel, sometimes described as multi-messenger astronomy, combining traditional light-based observations with gravitational wave detections and, in select cases, particle detections like neutrinos, to build a far more complete picture of extreme cosmic events than any single method could provide alone. The relevance to everything discussed so far is this: inflation, if it happened, would have generated its own background of gravitational waves, stretched across the entire universe in the same way the cosmic microwave background represents stretched light from the early universe. That primordial gravitational wave background is, in principle, the same signal researchers are hunting for indirectly through the B-mode polarization search described earlier. But some physicists hold out hope that future, far more sensitive gravitational wave detectors, potentially including proposed space-based observatories designed to detect much lower frequency waves than LIGO can currently access, might eventually be able to search for hints of this primordial signal more directly. This remains a genuinely long-term prospect, requiring technology considerably beyond what currently exists, but it represents another example of how cosmologists are not simply waiting passively for the universe to reveal its secrets. They are actively developing entirely new categories of instruments specifically designed to catch signals that traditional telescopes, restricted to detecting only light, could never access in the first place. So the picture so far is already strange enough. We live inside a shrinking window of visibility in a cosmos that appears to be actively erasing the majority of itself from our potential future knowledge. But this raises an even more basic question that we still have not addressed. How big is the universe actually? Not just the part we can see, but the whole thing. And this is where cosmology shifts from talking about what we can observe to talking about what we can only infer. The most direct clue comes from something called the cosmic microwave background, often abbreviated as the CMB, the faint afterglow of the Big Bang itself. Radiation that has been traveling through space since the universe was only about 380,000 years old, the moment when the universe cooled enough for light to travel freely for the first time. This radiation was first detected almost by accident in 1965 by two Bell Labs engineers, Arno Penzias and Robert Wilson, who were troubleshooting a persistent hiss of radio noise in their antenna, initially blaming it on pigeon droppings before realizing they had stumbled onto direct evidence of the universe's infancy, a discovery that earned them the Nobel Prize. What makes the Penzias and Wilson discovery so satisfying from a scientific storytelling perspective is that it did not happen in a vacuum. For decades, cosmology had been split between two competing pictures of the universe. Before either Lemaitre or Hubble entered the picture, a Russian mathematician and meteorologist named Alexander Friedmann had already worked out, purely from theory, that Einstein's equations of general relativity, left unmodified by any artificial static term, naturally permitted an expanding universe as a valid solution. Friedmann published this work in the early 1920s, several years before any observational evidence existed to support it, and reportedly exchanged skeptical correspondence with Einstein himself, who initially believed Friedmann had made a mathematical error, before eventually conceding the mathematics was sound. Even though Einstein still doubted it described physical reality, Friedmann died of typhoid fever in 1925, only in his 30s, never living to see Hubble's observations vindicate his purely theoretical prediction. It is a quietly poignant footnote in the history of cosmology. A correct answer arrived at years ahead of the evidence needed to confirm it by someone who did not survive long enough to know he had been right. One, the Big Bang model, championed in its early mathematical form by physicist Georges Lemaitre, a Belgian Catholic priest and astronomer working independently of Friedmann, and arriving at broadly similar conclusions a few years later, while also being the first to explicitly propose that running the expansion backward implied the universe originated from what he called a primeval atom, and later developed further by George Gamow and his collaborators, proposed that the universe began in an extremely hot, dense state and had been expanding and cooling ever since. Gamow and his students, Ralph Alpha and Robert Herman, went so far as to calculate in the 1940s that if this model were correct, the early universe's heat should have left behind a faint, cooled remnant of radiation now stretched by expansion into the microwave range, filling the entire sky almost uniformly. Their prediction was for years largely overlooked. The competing model, called the steady-state theory, developed by astronomers including Fred Hoyle, Hermann Bondi, and Thomas Gold, proposed instead that the universe had no beginning at all, that it had always existed and always would, expanding eternally, while new matter continuously and spontaneously appeared to keep the average density constant over time. It is a strange historical footnote that the term Big Bang itself was actually coined by Fred Hoyle, one of the theory's most prominent opponents. During a radio broadcast intended somewhat dismissively, though the name stuck and lost its mocking connotation over time, the two theories remained genuinely competitive for years, each with capable defenders, until Penzias and Wilson's accidental discovery of that persistent microwave hiss, later confirmed, to match almost exactly the radiation Gamow's team had predicted decades earlier, provided the kind of direct, physical evidence that a steady-state universe simply could not explain. The debate did not end instantly. Science rarely works that cleanly. But the discovery marked a decisive turning point, and within a relatively short span of years, the Big Bang model became the accepted framework it remains today, while steady-state theory faded into the category of historically important but ultimately unsupported alternatives. Since then, a series of increasingly precise satellite missions, the Cosmic Background Explorer in the early 1990s, the Wilkinson Microwave Anisotropy Probe in the 2000s, and the Planck satellite in the 2010s, have mapped this ancient light with extraordinary detail, revealing tiny temperature fluctuations, differences of only millionths of a degree, that represent the seeds from which all future galaxies and cosmic structure eventually grew. But buried within that map is another kind of information entirely, something about the very shape of space. Before getting into the mechanics of how curvature is actually measured, it helps to understand a foundational assumption underlying nearly all of modern cosmology, an assumption so deeply embedded that it rarely gets stated explicitly outside of textbooks. It is called the cosmological principle, and it holds that on sufficiently large scales, the universe is both homogeneous, meaning it looks roughly the same everywhere, and isotropic, meaning it looks roughly the same in every direction. This is, in essence, a modern extension of the Copernican principle, the idea first forced upon humanity by Copernicus's heliocentric model that Earth does not occupy any special privileged position in the cosmos. Copernicus removed Earth from the center of the solar system. Later observations removed the Sun from the center of the galaxy, revealing it to be an unremarkable star roughly 2/3 of the way out along one spiral arm of the Milky Way, and the discovery that the Milky Way itself is just one ordinary galaxy among a vast population of others, removed even our galaxy from any claim to cosmic centrality. The cosmological principle represents the logical endpoint of this progression, the working assumption that no observer anywhere in the universe, on any planet orbiting any star in any galaxy, occupies a privileged vantage point, and that the large-scale structure and behavior of the cosmos should appear statistically similar no matter where you happen to be standing to observe it. This is not simply philosophical modesty for its own sake. It functions as a testable and remarkably well-supported scientific assumption. Large-scale surveys mapping the distribution of galaxies across enormous volumes of space consistently find that once you average out local clumping into galaxy clusters and superclusters, matter is distributed with striking uniformity on the largest observable scales. The cosmic microwave background arriving from every direction in the sky with almost identical temperature and statistical properties provides perhaps the strongest evidence of all for isotropy specifically. Without the cosmological principle, in fact, much of the mathematics used to model cosmic expansion and curvature would not even be tractable, since it relies on treating the universe as describable by a relatively simple, uniform geometry rather than an impossibly complex patchwork requiring a unique description for every location. It is worth noting that the cosmological principle is a working assumption validated by observation on large scales, not a law derived from first principles, and cosmologists remain alert to any evidence that might reveal meaningful large-scale anisotropy, occasional claims of which surface periodically in the research literature, though none have so far overturned the overall picture. Here is the concept. If you send two beams of light out from the same point, perfectly parallel to each other, what happens to them over enormous distances depends entirely on the overall curvature of the universe. If the universe is shaped like a sphere, a positively curved geometry, those parallel beams would eventually converge, similar to how two lines of longitude that start parallel at the equator eventually meet at the poles. If the universe is shaped like a saddle, a negatively curved geometry, those beams would diverge, spreading further apart the farther they travel. But if the universe is flat in the geometric sense, meaning it follows the ordinary Euclidean rules you learned in school, those beams would remain perfectly parallel forever, never converging, never diverging. Astronomers can effectively test which of these scenarios matches reality by examining the sizes of the temperature fluctuations imprinted in the cosmic microwave background. Because the physics of the early universe predicted a specific characteristic size for these hot and cold spots, based on the distance sound waves could travel through the early cosmic plasma before the universe became transparent. By comparing the actual observed angular size of these spots in the sky to the size predicted if space were flat, scientists can measure curvature directly. And the results, refined over decades of increasingly precise satellite data, consistently point to one answer. The universe appears to be flat, or so close to flat that current instruments cannot detect any meaningful deviation. The most precise measurements from the Planck satellite constrain any curvature to within about a fraction of a percent of perfectly flat geometry. To appreciate why this flatness, result struck physicists as so significant, it helps to understand just how sensitive the early universe's geometry actually was to tiny variations. Run the equations of standard Big Bang cosmology backward in time, and it turns out that for the universe to appear as close to flat as it does today, its density in the earliest fractions of a second after the beginning would have needed to match a very precise critical value to an accuracy of something like 1 part in 10, followed by dozens of zeros, a degree of fine-tuning so extreme that physicists generally treat any theory requiring that level of coincidental precision as a sign that something deeper must be going on, some underlying mechanism forcing that value toward flatness naturally, rather than accepting it as a wildly improbable accident of initial conditions. This is precisely the flatness problem inflation was built to resolve, and it is worth returning to now that the observational result is on the table, because it shows how the theoretical problem and the observational result reinforce each other from opposite directions. One predicting that flatness should emerge naturally from a specific physical mechanism, the other confirming through completely independent measurement that the universe really is flat to within our best current precision. This might sound like a satisfying, tidy answer, but it actually opens up one of the strangest implications in this entire subject. A universe that is truly perfectly flat with zero curvature is mathematically consistent with being infinite in extent. Flatness does not require infinity. Technically, a flat universe could still be finite if space wraps back around on itself in complex topological ways, similar to how the surface of a video game screen can be flat yet finite, with objects exiting one edge reappearing on the opposite side. But if the universe is flat and does not have this kind of wraparound structure, infinite is the natural, simplest interpretation. However, and this is the crucial nuance that separates careful science from overconfident headlines, precision is not the same as certainty. Current measurements tell us the universe is flat within an extremely small margin of error, but that margin of error still leaves room for the universe to be closed, meaning finite but unbounded, curving back on itself like the surface of an enormous four-dimensional sphere, provided that sphere is large enough. Calculations based on the current observational limits suggest that if the universe is closed, its total radius would need to be at least 250 times larger than the radius of our observable universe, and quite possibly dramatically larger still. In other words, even in the scenario where the universe is technically finite, it would still be so vast that the difference between a finite universe of that scale and a truly infinite one becomes almost meaningless from any practical or observational standpoint. We would still never come close to seeing more than an infinitesimal fraction of it. This is worth sitting with. Multiple independent lines of evidence point toward a universe that is either infinite or so close to infinite that no experiment we can currently imagine could ever tell the difference. And yet, because of the cosmological horizon we discussed earlier, we are permanently restricted to observing only a single, comparatively tiny bubble within that vastness. We have strong theoretical reasons to believe the true universe dwarfs the observable one, potentially by factors so large that ordinary numbers stop being useful for describing them. And simultaneously, we have a hard physical barrier guaranteeing we will never obtain direct evidence of what lies beyond a certain point. Two extraordinary claims, both extremely well supported, that combine to produce a genuinely uncomfortable scientific situation, permanent uncertainty about the most basic possible question you can ask about existence. To understand why physicists suspect the universe is so enormously larger than what we can see, even beyond what the flatness measurements alone suggest, we have to go back to the first fraction of a second after the Big Bang, to a theory called cosmic inflation. In the late 1970s and early 1980s, physicists including Alan Guth, working independently alongside contributions from Andrei Linde and others, were trying to solve several nagging problems with the standard Big Bang model. One of those problems was exactly the flatness issue we just discussed. Why would the universe happen to be so close to perfectly flat when in principle it could have taken on any curvature at all? Left purely to chance, a flat universe seemed like an extraordinarily unlikely coincidence, similar to balancing a pencil perfectly on its tip and having it stay there indefinitely. Another problem involved the uniformity of temperature across the cosmic microwave background. Regions of the sky on opposite sides of the observable universe. Regions that under standard Big Bang expansion should never have had enough time to physically interact or exchange information with each other, nevertheless show almost identical temperatures. How could regions that were never in causal contact end up so similar? Before turning to inflation itself, it is worth being honest about exactly how far back in time our physical theories can currently reach with any confidence, because the answer reveals another, quieter kind of horizon, this one in time rather than in space. Standard Big Bang cosmology, combined with well-tested particle physics, allows scientists to describe the universe's history with reasonable confidence back to roughly 1/100th of a second after the beginning, and with somewhat less certainty back through the earlier stages of inflation itself, but push further back still into what is called the Planck epoch, the interval before roughly 10 to the negative 43 seconds after the beginning, and current physics simply runs out of tools. At those energy scales, the effects of quantum mechanics and general relativity, our two most successful physical theories, would both become significant simultaneously, and no one currently possesses a complete, experimentally verified theory of quantum gravity capable of describing what happens when both frameworks matter at once. Candidate theories exist, string theory and loop quantum gravity being the two most extensively studied, each proposing different pictures of what might replace ordinary notions of space and time at these extreme scales. But neither has been experimentally confirmed, and some critics argue neither may ever be directly testable given the almost unreachable energy scales involved. This means that questions like what caused the Big Bang, or what, if anything, existed before it, currently sit beyond the boundary of what physics can rigorously address. Not necessarily forever, but certainly with the tools and theories available today. Any documentary or article that confidently narrates the very first instant of the universe's existence, describing it as a single infinitely dense point, for instance, is, strictly speaking, extrapolating past the edge of currently verified physics. The honest answer to what happened at the very beginning, before the Planck epoch ends and standard cosmology can take over the narrative with confidence, is that nobody currently knows, and saying so plainly is a feature of good science communication. Not a shortcoming of it, Alan Guth arrived at this idea somewhat by accident. A young particle physicist bouncing between postdoctoral positions in the late 1970s, Guth was not initially working on cosmology at all. He was studying a class of hypothetical particles called magnetic monopoles, isolated north or south magnetic poles, that certain particle physics theories predicted should have been produced in enormous numbers during the extreme conditions of the early universe, yet had never once been observed anywhere in nature despite decades of searching. This mismatch, a theoretical prediction of abundant monopoles against an observational reality of zero detected monopoles, became known as the monopole problem, a third puzzle sitting alongside the flatness problem and what is called the horizon problem, the uniformity issue we described earlier, involving regions of the cosmic microwave background that appear to share a temperature despite, under standard expansion alone, never having had time to exchange any information or heat with each other. While working through the physics of an early universe phase transition in December of 1979, Guth realized that a brief period of exponential expansion occurring before the standard Big Bang expansion took over would elegantly dilute any monopoles down to an undetectably low concentration, spreading whatever few existed across an enormously larger volume of space, while simultaneously solving the flatness and horizon problems as a natural side effect. Guth reportedly wrote the words "spectacular realization" in his research notebook that night, a rare moment of a scientist recognizing in real time that they had stumbled onto something significant. Goethe's proposed solution was audacious. What if, in an incredibly brief instant after the Big Bang, somewhere around 10 to the negative 36 seconds after the beginning, the universe underwent an extraordinarily rapid burst of expansion, growing by a factor of at least 10 to the 26 in a fraction of a second, before settling back into the more gradual expansion rate we associate with the aftermath of the Big Bang. This period, called cosmic inflation, would elegantly solve both problems at once. Any initial curvature in the universe would have been stretched flat, in exactly the same way that the surface of a balloon looks progressively flatter to an ant standing on it as the balloon inflates larger and larger. And regions that appear too uniform to have ever been in contact would actually have been in close contact before inflation dramatically stretched the distances between them, essentially freezing in a uniform temperature before blowing everything apart to cosmic scales. One of inflation's most elegant contributions involves explaining not just why the universe is flat and uniform, but where the tiny irregularities that eventually grew into galaxies actually came from in the first place. A perfectly uniform universe, after all, would never have developed any structure at all. No galaxies, no stars, no planets, just an eternally smooth, featureless soup of matter and energy. Something needed to seed small variations in density, tiny regions slightly denser than their surroundings, whose extra gravity could then attract more matter over time, snowballing into the galaxies and galaxy clusters we see today. Inflation offers a genuinely elegant answer rooted in quantum mechanics. Before and during the inflationary period, the universe was governed by quantum fields, and quantum fields are never perfectly smooth. They inherently fluctuate at the smallest scales, a direct consequence of the uncertainty principle central to quantum theory. Under ordinary circumstances, these fluctuations would remain microscopic, popping in and out of existence at subatomic scales without ever mattering to anything larger. But during inflation's extraordinarily rapid expansion, these tiny quantum fluctuations were stretched almost instantly, from subatomic scales up to sizes spanning entire future galaxies and galaxy clusters, effectively freezing microscopic quantum randomness into macroscopic differences in density across the early universe. Those frozen fluctuations are precisely what shows up as the tiny temperature variations in the cosmic microwave background, and precisely what eventually grew over hundreds of millions of years of gravitational amplification into every galaxy, star, planet, and eventually into the very matter making up anyone listening to this. In a very real sense, the large-scale structure of the entire universe traces back to quantum randomness magnified to cosmic proportions, an idea that sounds almost too strange to be taken seriously, yet is supported by detailed statistical agreement between predicted and observed patterns in the cosmic microwave background data. Inflation has since become one of the most widely accepted frameworks in cosmology, not because it has been directly observed in some singular smoking gun experiment, but because it successfully predicted several subtle features later confirmed in the cosmic microwave background data, including the precise statistical pattern of those temperature fluctuations we mentioned earlier. It is important to be clear about the current state of the evidence here. Inflation is strongly supported as a theoretical framework, consistent with an impressive range of observations, but it remains, in certain specific details, an active area of research rather than a fully settled fact in every particular. Multiple versions of inflationary theory exist, differing in their specifics, and scientists continue working to narrow down exactly which version, if any, precisely matches reality, in part by searching for a very particular signature, a pattern of polarized light called B-mode polarization in the cosmic microwave background, which would represent indirect evidence of gravitational waves generated during inflation itself, essentially faint ripples in space-time stretched and frozen into the polarization pattern of the oldest light in existence. Detecting this signal cleanly has proven extraordinarily difficult. in large part because foreground contamination, polarized light scattered by dust within our own Milky Way galaxy, produces a similar-looking signature that has to be carefully modeled and subtracted before any genuine primordial signal could be confirmed. Ground-based experiments in Antarctica and Chile have spent years refining this search, and a dedicated satellite mission named Lightbird, a collaboration led by the Japan Aerospace Exploration Agency in partnership with international partners, is currently in development with the specific goal of achieving the sensitivity needed to detect or definitively rule out this signal at the level predicted by the simplest inflationary models, representing one of the clearest near-term opportunities to move some of the most speculative aspects of this entire subject from theoretical inference towards something closer to direct evidence. But if inflation in some form is correct, it carries an implication that stretches far beyond merely explaining our own observable universe's flatness and uniformity. Because if a region of space could inflate by a factor of 10 to the 26 or more in a fraction of a second, there is no obvious reason why that inflationary process would have started and stopped everywhere, uniformly, all at once, across all of existence. In fact, many of the most well-studied versions of inflationary theory suggest something closer to the opposite. Inflation, once triggered, tends to be extremely difficult to stop completely everywhere at the same time because the underlying quantum field driving the expansion behaves probabilistically. In regions where inflation ends, pockets of ordinary space and matter form, essentially becoming their own separate universes with their own Big Bang-like origins. But in the regions where inflation does not end, the space itself keeps expanding exponentially, faster than the process of ending inflation can catch up with it. This leads to a genuinely mind-bending framework called eternal inflation, developed and refined by physicists including Andrei Linde and Alexander Vilenkin, among others. Under this model, inflation never actually stops globally. It only stops locally within isolated regions which then become bubble universes, each with their own version of a Big Bang, embedded within an ever-expanding, eternally inflating background. Our entire observable universe, everything we have discussed so far, 93 billion light-years across, potentially far larger still, if the universe truly is spatially infinite or extremely vast, might be nothing more than the interior of a single bubble within an unimaginably larger structure, sometimes called a multiverse, filled with countless other bubble universes, each one forever separated from every other by the relentless expansion happening in the space between them. It is critically important to be precise about where this idea sits on the spectrum from established science to speculation. Eternal inflation is a serious, mathematically rigorous extension of inflationary theory taken seriously by many working cosmologists, and it emerges relatively naturally from the same equations that explain features we have already confirmed observationally. But it is not, at this point, something that can be directly tested or verified, and it may never be, precisely because of the same cosmological horizon problem we discussed earlier. If other bubble universes exist, the space between our bubble and theirs is expanding far too rapidly for any signal, any light, any information whatsoever to ever cross the gap and reach us. It is a theory that follows logically from well-supported physics, but it makes a prediction, the existence of other universes, that appears to be permanently unfalsifiable by any observation we could ever hope to make. This puts eternal inflation in a genuinely unusual category, taken seriously by serious scientists, while simultaneously existing outside the traditional boundary of what most philosophers of science would call empirically testable. And this brings us to the deeper, almost philosophical shift happening quietly within modern physics. For most of scientific history, the gold standard of knowledge has been observation. You propose a hypothesis, you design an experiment or observation that could, in principle, prove it wrong, and if it survives repeated attempts at falsification, confidence in that hypothesis grows. But cosmology, dealing as it does with the single largest possible object of study, all of existence, has increasingly run into questions where direct falsifying observation is either currently impossible or permanently impossible, not due to any lack of ingenuity, but due to the actual physical structure of reality itself. In response, an increasing number of cosmologists have leaned into a different, complementary standard, mathematical and theoretical consistency. If a model like inflation successfully explains and predicts a wide range of things we can observe, the flatness of space, the uniformity of the cosmic microwave background, the specific statistical pattern of tiny fluctuations that seeded galaxy formation, then its untestable implications, like the existence of other bubble universes beyond our horizon, gain a kind of second-hand credibility, not because they have been directly confirmed, but because they emerge unavoidably from the same framework responsible for everything else that has been confirmed. This is sometimes described as inference to the best explanation, treating a theory's broader implications as reasonably likely to be true if the theory itself has proven remarkably successful in every testable respect. It is a more cautious, more honest form of confidence than outright proof, and any responsible presentation of this subject needs to make that distinction clear. Believing eternal inflation is plausible because inflation itself is well supported is very different from claiming eternal inflation has been proven. It has not, and given the physics involved, it likely never can be in any direct sense. It is worth pausing here to be clear about how many distinct ideas get grouped together under the casual label of a multiverse, because conflating them tends to muddy the science considerably. Physicist Max Tegmark proposed a useful, though admittedly informal, classification that separates these concepts by how speculative and how testable each one is. What we have been describing so far, other regions of space lying beyond our cosmological horizon but still governed by the same laws of physics as our own region, sometimes called a level 1 multiverse in this classification, is really just an extension of the well-supported idea that space is far larger than what we can observe, differing from our own observable universe only in the specific arrangement of galaxies and stars it happens to contain, not in its underlying physical laws. This is the least speculative version, following almost directly from an infinite or extremely large flat universe. The bubble universes produced by eternal inflation, sometimes called a level 2 multiverse, are more exotic still because different bubbles, having undergone their own independent process of inflation ending, could in principle end up with different effective physical constants, different strengths of fundamental forces, even different numbers of large spatial dimensions, depending on the specific details of how the underlying inflationary field settled down within each bubble. One place this idea of varying constants across different bubble universes gains additional theoretical support, beyond eternal inflation alone, comes from string theory, one of the leading candidate frameworks for unifying quantum mechanics and gravity mentioned earlier. Certain versions of string theory suggest that the specific mathematical structure of extra-spatial dimensions, dimensions beyond the 3 we experience directly, curled up at scales far too small to detect, can take on an enormous number of distinct possible configurations, sometimes estimated at figures as large as 10 followed by 500 zeros. Each distinct configuration would correspond to a different resulting set of effective physical constants in the larger, 4-dimensional universe that emerges from it, a vast collection of possibilities researchers have taken to calling the string theory landscape. Combine that landscape of possible configurations with eternal inflation's mechanism for generating countless separate bubble universes, and you get a natural, if still entirely speculative, explanation for why different bubbles might end up with different physical constants in the first place. Each bubble effectively rolling a very large, very complicated die during its own formation and settling into one particular configuration out of an almost incomprehensibly vast number of possibilities. It is worth repeating that none of this landscape has been observationally confirmed, and it remains a subject of genuine, sometimes sharp disagreement even among theoretical physicists. some of whom view it as a promising unifying framework, and others who view an unfalsifiable landscape of possibilities as a sign the underlying theory has drifted too far from anything experimentally testable to be considered fully scientific in the traditional sense. Beyond this, some physicists have speculated about even stranger possibilities entirely disconnected from inflationary cosmology, involving quantum mechanics or abstract mathematics rather than cosmic expansion, ideas considerably further removed from direct observational grounding and genuinely contested even among physicists sympathetic to the general idea of a multiverse. It is important to state plainly that none of these levels beyond the first have been observationally confirmed, and the more exotic versions remain, for many physicists, more a matter of philosophical interest than active experimental research. Bringing this up is not an endorsement of speculative multiverse theories as established fact, but rather a way of showing how a single popular idea actually contains a whole spectrum of claims, ranging from nearly certain to almost entirely untestable, and a responsible treatment of this subject has to keep those distinctions intact rather than blurring them together into one dramatic package. One additional wrinkle worth mentioning, since it comes up frequently in discussions of a multiverse with varying physical constants, is a genuinely contested piece of reasoning called the anthropic principle. In its most defensible form, the anthropic principle simply notes that any universe we happen to observe must, by definition, be one capable of supporting observers in the first place. Since a universe with, for example, dramatically different values for fundamental constants of nature, values that prevented atoms, stars, or chemistry more generally from forming, would never produce anyone around to notice it. If a level 2 style multiverse does exist, populated with countless bubble universes each having different physical constants determined somewhat randomly during their own individual inflationary histories, the anthropic principle would explain why we find ourselves in one of the comparatively rare bubbles where conditions happen to allow complex structure and life to exist, without requiring any deeper explanation for why those particular constants were selected. Critics, and there are many serious ones within physics and philosophy of science alike, argue that this reasoning risks becoming unfalsifiable in a different, more troubling way than the multiverse hypothesis itself, potentially explaining away any observation whatsoever after the fact, rather than making genuine predictions in advance that could be tested and potentially proven wrong, which is generally considered the defining feature of a rigorous scientific explanation. This remains an active, sometimes heated debate within theoretical physics and philosophy of science, and it is presented here not as a settled resolution to anything, but as an honest look at the kind of reasoning physicists reach for when grappling with questions that current observational tools simply cannot adjudicate directly. This tension between what we can theoretically justify and what we can actually confirm defines much of contemporary cosmology, and it forces scientists into an unusual intellectual position, comfortable holding strong, well-reasoned beliefs about aspects of reality they know, with total certainty they will never be able to directly verify. It requires a kind of humility that runs counter to how science is often portrayed in popular culture, where every mystery eventually gets solved by a clever enough experiment. Some mysteries, cosmology increasingly suggests, may be permanently structural, built into the very geometry of an expanding universe, immune to any conceivable advance in technology or cleverness. Consider what this means on a human scale. Every civilization that will ever exist in this universe, no matter how technologically advanced, no matter how many millions of years it has to develop new instruments, will face the exact same fundamental restriction we face today, a horizon beyond which information simply cannot travel, growing more restrictive, not less, as time passes and dark energy continues driving space apart. There is no clever experiment on the horizon that solves this. There is no future telescope, however powerful, that circumvents it. This is not a temporary gap in human knowledge waiting to be filled. It appears to be a fundamental and permanent boundary condition of the reality we happen to inhabit, and yet there is something worth appreciating in this limitation rather than simply mourning it. The fact that we can even calculate the existence of this horizon, that we can reason our way to understanding its implications despite never being able to directly observe what lies beyond it, is itself a remarkable testament to the power of mathematics and physical theory. We are, in a very real sense, mapping the unreachable using nothing but careful observation of the reachable, extending our understanding through logical inference into territory our eyes and instruments will never physically access. Humanity figured out the age of a universe we cannot directly perceive in its entirety. We figured out the existence of a boundary we cannot see by studying the light that has managed to cross it before that boundary closed around it. We inferred an inflationary period that happened in a fraction of a second 13 billion years before any human existed by examining subtle statistical patterns in ancient light. That is not a small achievement. It represents one of the most impressive intellectual feats our species has managed, figuring out the shape and history of something we are permanently, physically barred from ever fully seeing, what remains genuinely unresolved, and what current and near-future research is actively working to narrow down, falls into several distinct categories. First, the exact nature of dark energy, the mysterious force driving accelerated expansion, remains almost entirely unknown. We can measure its effects with growing precision, but we do not know whether it represents a constant property of empty space itself, sometimes called the cosmological constant. Originally proposed and later abandoned by Einstein himself before observations forced its return, or whether it represents something more dynamic, a field whose strength changes over cosmic time. Missions like the Dark Energy Spectroscopic Instrument, an Earth-based survey that has already mapped the three-dimensional positions of tens of millions of galaxies and quasars, have recently produced results hinting, though not yet conclusively proving, that dark energy's strength might be evolving over billions of years rather than remaining perfectly constant. A finding that, if confirmed by future data from Euclid and the Roman Space Telescope, would represent one of the most significant shifts in cosmology in decades. The technique behind this instrument's measurements deserves a brief explanation, because it represents one of the more ingenious tools in modern cosmology, a natural ruler baked into the universe itself. In the early universe, before atoms had fully formed, ordinary matter existed as a hot, dense plasma, and pressure waves, essentially sound waves, rippled through this plasma the same way ripples spread outward from a stone dropped into a pond. When the universe cooled enough for neutral atoms to form, roughly 380,000 years after the beginning, these pressure waves suddenly froze in place, leaving behind a faint but statistically detectable preference for galaxies to form at a very specific characteristic separation distance from each other, corresponding to how far those ancient sound waves had traveled before freezing. This imprint is called the baryon acoustic oscillation signal, and because the size of that characteristic separation distance can be calculated from first principles based on early universe physics, astronomers can use it as a standard ruler. Comparing its known true size to its apparent size at different distances and redshifts across billions of years of cosmic history, in order to precisely measure how the expansion rate of the universe has changed over time. It functions as a companion technique to the standard candle method using supernovae, one relying on a known brightness, the other on a known length, both converging on the same fundamental goal: reconstructing the detailed expansion history of the universe with enough precision to catch subtle deviations, like the possible evolution of dark energy strength, that a single method alone might miss or misattribute to other sources of error. Second, the Hubble tension. That persistent disagreement between early universe and late universe measurements of the expansion rate remains unresolved, and its eventual resolution could either reveal a subtle measurement error finally being corrected, or it could reveal genuinely new physics operating in ways current theory does not yet account for. Third, And perhaps most fundamentally, the question of whether cosmic inflation is correct in its details, and whether the more speculative extension of eternal inflation reflects anything real about the broader structure of existence beyond our observable bubble, remains genuinely open, likely to remain open for the indefinite future, constrained by exactly the kind of permanent observational horizon we have spent this entire discussion exploring. Fourth, researchers continue refining the search for that elusive B-mode polarization signature in the cosmic microwave background, the potential fingerprint of gravitational waves generated during inflation itself. Ground-based efforts, including the Simons Observatory, a network of telescopes situated in the high-altitude Atacama Desert of Chile, chosen specifically for its dry, stable atmosphere ideal for microwave observations, alongside the proposed CMBS-4 collaboration bringing together multiple institutions and telescopes across both hemispheres, are steadily pushing sensitivity to this signal higher year after year. Combined with the Light-Bird satellite mission expected to launch by the early 2030s, specifically designed to be free of the atmospheric interference that limits ground-based observatories, the coming decade offers a genuine, non-trivial chance of either detecting this signature directly, providing striking new evidence in support of inflation's most basic prediction, or ruling out entire families of inflationary models that would have produced a signal strong enough to detect, narrowing the theoretical landscape considerably either way. This is refreshingly an example of a cosmological question that current and near-future technology can actually make direct progress on. Unlike the permanently unreachable regions beyond the cosmological horizon itself. Fifth, there remains the sobering question of where all of this ultimately leads, the long-term fate of a universe dominated by accelerating expansion. Assuming dark energy continues behaving as current evidence suggests, roughly constant in strength, models point toward a scenario cosmologists sometimes call the Big Freeze or heat death, an almost unimaginably gradual process stretching across trillions upon trillions of years. Star formation, which requires clouds of gas dense enough to collapse under their own gravity, will slowly wind down as galaxies exhaust their available raw material, with the last very faint, small, slow-burning red dwarf stars, the most fuel-efficient stars in the universe, finally flickering out perhaps at some point roughly 100 trillion years from now, an era astronomers sometimes call the end of the stelliferous era. After that, the universe enters an increasingly dark epoch dominated first by dim stellar remnants, white dwarfs, neutron stars, and black holes, and eventually, over spans of time so large that human numerical intuition genuinely fails to grasp them. Even those remnants may eventually evaporate or decay according to speculative but theoretically motivated physics, leaving behind an almost perfectly empty, cold, dark universe expanding forever into a de Sitter-like future, precisely mirroring that decades-old mathematical toy model we discussed earlier, no longer a curiosity but potentially the genuine final state of everything. It is worth emphasizing that this specific long-term outcome depends entirely on dark energy's true nature remaining what we currently believe it to be, and if the ongoing research into whether dark energy is evolving over time turns out to reveal something different, the ultimate fate of the universe could look considerably different too. A reminder that even our best long-range forecasts remain provisional. Contingent on physics we have not yet fully pinned down, there is something almost poetic in where this leaves us. We began by asking a seemingly simple question. How big is the universe? And we end not with a number, but with an honest accounting of the limits of numbers themselves, a recognition that some of the most important truths about existence may be truths we can approach, reason toward and mathematically justify, without ever being able to point a telescope at them and see them directly for ourselves. The observable universe, that 93 billion light-year sphere surrounding us, is not a boundary imposed by our own limitations. It is not something better engineering will eventually overcome. It appears to be a genuine edge of knowability itself, carved into the geometry of space-time by the same accelerating expansion that will, over unfathomable stretches of future time, continue closing in around whatever remains to observe it. What we know for certain is this: space is expanding, and that expansion is accelerating, driven by a force we can measure but not yet explain. What we can observe of the universe represents only a fraction, potentially an infinitesimally small fraction, of what actually exists. The boundary separating what we can see from what we cannot is not static, but actively shrinking our future field of view with each passing year. And the deepest question of all, exactly how large or how infinite the true universe actually is, sits permanently beyond the reach of direct proof. A mystery, not because we have failed to look hard enough, but because the universe itself, through the very physics that allows stars, galaxies, and eventually curious minds capable of asking these questions to exist in the first place, has ensured that certain answers will always remain just beyond the horizon. Perhaps that is not a failure of science, but a reminder of exactly how much larger reality is than the small, precious window we have been given to study it. It is a strange kind of privilege when you sit with it long enough to be a brief, temporary arrangement of atoms capable of looking outward, doing the math and understanding even partially, even provisionally, the shape of a horizon it will never personally cross. Every generation of astronomers before us worked with a smaller, cruder picture of the cosmos, and every generation after us will very likely work with a picture sharper, more precise and more complete than the one available today, refined by instruments not yet built, using techniques not yet invented, answering questions not yet fully formed. What will not change, no matter how far that future knowledge advances, is the underlying architecture of the problem itself. A universe expanding faster than light can cross it, quietly, permanently placing the overwhelming majority of itself forever out of reach. That is not a flaw in the story. It might be the most honest thing science has ever said about the true scale of what we are actually a part of. And somewhere out there, right now, past every horizon we will ever calculate, entirely indifferent to whether we ever manage to prove it, the rest of the universe simply continues on, exactly as real as the small sliver we happen to call home.